Let's talk a little bit about inference. Now, inference is covered in modules 5 and 6, as well as the latter half of your textbook. Now, inference is basically breaks down to two key types of questions. We're going to have confidence intervals and we're going to have hypothesis tests. Confidence intervals are a way for us to develop an estimate about the population, some characteristic of the population. We're going to make an inference about the population based on some information we gather from a sample, hopefully a representative sample. So those types of questions will be like, we want to estimate the true average height of Canadians. So based on this sample of Canadians, we found they have an average height of like 1.6 meters or whatever. And how can we be 95 or 90 or 99% confident? Generally, a confidence interval will ask us for some percentage of confidence, some assuredness. That'll give us an idea of how precise we want to be in our estimate. And those will be those types of questions. And what we do when we build these ranges, we're always doing a point estimate. And for us, our point estimate is always going to be the sample mean and a margin of error, which will either use Z or T and the standard error of X times the standard error of X. And we'll talk a little bit more about what, how we know whether it's Z or T or whatnot. But these will always be based on an alpha over 2 because we'll be testing in two directions, and T will have n-1 degrees of freedom. Now, a hypothesis test is where we're drawing an inference based on what we assume or know about the sample. We want to know whether or not a means of a sample is different than the population. So this might be, is this subset different than the rest of the population? Or a lot of times it'll be we've done something, right? So we've changed a process, we've changed something. So does this change the mean? So these questions will always be, are we confident that there's some statistical difference, that something has changed, that this one sample is different than the population or the previous way we used to do it before. So we might see questions like, is this, does, based on the evidence we see, or can we be, do we have evidence that the alpha equals 0.01 level of significance to say that, Canadian teenagers smoke more than teenagers worldwide, or based on this sample of a bunch of kindergartners who've gone through a different reading curriculum, do we have evidence that the alpha equals 0.1, the level of significance, to say that this program improves the reading comprehension of kindergartners? So we're comparing a sample to a population as a whole. We're testing against a known or assumed value. These will always have a null and alternate hypothesis. The null hypothesis will always be that nothing changes. The alternate hypothesis will always be something changed. Then we're going to develop a test statistic, which, depending on some characteristics, will either be T or Z. And then based on the alternate hypothesis, we'll develop a rejection criterion. This may involve with Z's going to the p-value, or with either we can just find a critical value that we reject if T is within a rejection range. So we'll develop a rejection range, which will be based on the alternate hypothesis. And then we draw a conclusion. Right? We conclude whether or not we reject H0 or fail to reject H0. And that'll be based on how this test statistic compares to the rejection range. Now, we have two specific types for confidence intervals and test statistics. We have what are called Z procedures and T procedures. Z procedures use the standard normal table. That's when we know we have a normal distribution. So if we are pulling a sample from a population we know is normally distributed, which is rare, but it can happen, then we always use Z procedures, right? We use Z procedures. If the population is large, we also can assume, because thanks to the central limit theorem, we can assume that the sampling distribution will be normal, so we can use Z procedures. So if n is greater than or equal to 30. T procedures are used when the sample size is small, so n is less than 30, or we have more than one sample. All right? There are Z procedures for more than one sample, but based on the modules, the curriculum for this course, we're going to use T procedures anytime we have more than one sample. Whether they're matched pair, the samples are drawn, they're linked in some way, or the samples are independently drawn. We're going to use that. So let's look at some of the formulas. So for confidence intervals, if we have one large sample, we use this confidence interval formula here. X bar, our point estimate, plus minus Z alpha over 2, the critical value. Sometimes I've called this Z star. I don't care which you use, whatever it is, times the sample standard deviation divided by the square root of n, or sometimes if population sigma is known, we just substitute the known population standard deviation in the place of the sample standard deviation. But this is a rare case, but I do want you to be aware of it. If we have a small sample, so our n is less than 30, we use the T procedure for it, which you'll notice is basically exactly the same. The only difference is instead of Z star, or Z alpha over 2, we use T alpha over 2, which can also be called T star. I'm not fussy on that notation, but T alpha over 2, which also relies on its degrees of freedom, which is n minus 1. So these are very similar. The only difference is where we get this value, right? Whether we use the Z value or the T value. But otherwise, the procedures are exactly the same for one sample, for sample size. Now, if we have two independent samples, this is strictly a T procedure. We don't have the Z procedure for it. Theoretically, you could just use, if these were large enough, you could just use the Z alpha over 2. But we won't worry about that. I'll allow you to do it if you do it on the final. But in general, try and stick to the T procedures the way it was shown in the modules. So what we do there is we take the mean of one, we subtract off the mean of the second sample, we have plus minus T alpha over 2, the T star value for the relevant degrees of freedom, relevant level of confidence, times the square root of the variance of sample 1 divided by the sample size of sample 1 plus the variance of sample 2 divided by the sample size of sample 2. So take that. That's confidence intervals. These are all the confidence interval formulas you'll need to know for the final. Now, hypothesis tests. Hypothesis tests always, no matter what you're doing, you're always going to have the same, you're going to develop in the exact same way a null and alternate hypothesis. And you're going to develop a rejection criterion based on what your alternate hypothesis comes out as, and what your test statistic, and compare it to your test statistic. Test statistic is really where we see the difference between Z procedures and T procedures, right? For an alternate hypothesis of the mean is less than the mean under the null hypothesis, so mu is less than mu naught. Our rejection criterion is always less than the critical value, or T is less, depending if you're using T, is less than negative of its critical value. The p-value is just the probability that Z is less than the test statistic Z. And I'll use this little cross to indicate the difference between Z's, the test statistics, and the capital Z's, which are the critical values. So, and you can, we only really can calculate p-values for Z's, but you can feel free to use the p-value method or the rejection criterion Z for either. So if it's the other way, if these are one-directional tests, right? We're testing to see, is the true mean smaller than our assumed mean, or the sample mean smaller than our assumed mean? Is the sample mean larger than our assumed mean? Then our rejection criterion is just as bigger than the critical value. And this can also be called Z alpha or Z, T alpha, depending, but I don't care. Whatever, as long as you're consistent when you're doing the final exam. So the p-value is P is Z is greater than the test statistic Z, which you'll know because our table reports it as Z less than Z is 1 minus the probability that Z is less than Z. Now, if we do a two-directional, right, we're not looking for is it bigger, is it larger, just is it different than This was Z alpha over 2. These are all alphas. I've used the T star value, but in this case, um, and it's the absolute value. We take the absolute value of the test statistic, and is it larger than the critical value for alpha over 2, because we're testing in two directions. The p-value is 2 times the probability that Z is greater than. Once again, the absolute value just means we ignore negatives. So these rejection criterion are exactly the same. The only thing that differs is where we get the critical values from and what we use to generate our test statistics. So if we have one large sample, our test statistic is just x bar, the sample mean, minus the assumed mean under the null hypothesis, mu naught, divided by the standard deviation, divided by the square root of the sample size n. Now, whether that standard deviation is the sample standard deviation or the known population standard deviation, that's possible, but it's rare, but you just plug it in. Now, if we have one small sample, we use the exact same formula, the exact same one. The sample mean minus the assumed mean under the null hypothesis divided by the sample standard deviation divided by the square root of n. We just call it t and we compare it to a different critical value. These are exactly the same formulas for one sample. So it's more than 30, less than 30, we use the same formula. It's just what we compare it to that will be different. We have different criteria for rejection. And we label this test statistics differently just to remind ourselves to use those appropriate rejection criteria. Now, we have two samples. These are all T procedures. They use the same rejection regions for T as one sample, but the test statistics are a little more complex. For two independent samples, it's the mean of sample 1 minus the mean of sample 2. Some implicit difference, assumed difference. Most of the time, this will be 0. There's very rare you come across cases where there's an assumed difference built into the question, but that's the way it's modified, divided by the square root of the variances divided by their respective sample size. So just divide by there. It's always just the difference in the means minus an assumption in the null hypothesis divided by the standard error. So matched pair is where, whereas this is we're drawing two samples in independent ways from two groups that don't really have contact. We're just randomly drawing them. Matched pair is where we draw the sample. We have two samples, but we're specifically targeting them. We might have the same person participate in both types, like they might be doing the old way and the new way, using some product, not using a different product, or using the product doing nothing, whatever it is, but we're specifically comparing these two things, but it's the same individual running through, or two participants we've chosen because they're linked so closely. They have characteristics that mean the only thing we're differing for those individuals going back and forth. And from there, we'll generate a difference statistic, which is just, if we have x under process A, x under process B, we have what are called our D's, which is just the value under A minus the value under B. Now, D bar is the average of all of those D's we'll generate. It's always D bar minus 0 divided by SD, which is the standard deviation of all those D's, the same way the mean and standard deviation of those differences, the same way we calculated them back in Module 1. Very, very straightforward, divided by the square root of n. We get that t-test statistic, and we use those same rejection criteria.